Okay, so this is video 16 on indirect derivation. So basically there are three techniques for derivation, and you should try them in this order. So first, try direct derivation. Direct derivation is always the easiest thing to do. So if you've got, you're just given a set of premises, and just start out by seeing what you can infer from them. And if you can get to the conclusion, you're fine. Second, if the want line is a conditional, use conditional derivation. And then finally, I have to write bigger now that I've switched to the Sharpie. If all else fails, use indirect derivation. Right? Direct derivation. Conditional derivation, if your want line's a conditional, that's the obvious sign. There might be other reasons you can try it. If all else fails, use direct derivation. Indirect derivation. So what is the deal with indirect derivation? Basically, the idea with indirect derivation is that you're going to assume the opposite of what you are trying to prove. You assume the opposite of what you are trying to prove. So this is some weird, like, jujitsu stuff, right? I mean, what's going on here? The secret is that what you're doing is you're saying, well, if this statement were false, something horrible would come out of it. Therefore, it must be true. You think about presidential campaigns like we've been seeing. Both sides say, if you elect my opponent, all hell will break loose. You know, the whole world will end. Well, what is the equivalent in logic of the whole world ending is a contradiction. So what essentially you're saying is you assume the opposite of what you're trying to prove and show it leads to a contradiction. So the schema is going to look like this. The schema is going to look like this right here. You assume A, and then you're going to mark it for reductio. And you can also say that you want a contradiction. Right? And then on the next two lines, or subsequent in the proof, you're going to show both a statement and its opposite, B and not B. And then from that, you can infer the opposite of what you started with, which was the thing you're looking for. So from A, you would get not A, because you've shown that A leads to a contradiction. And so this is the rule of negation introduction. The rule of negation elimination is almost exactly the same, except that the negation is on the other side. So you start out here with a negation. You write for reductio, want a contradiction. You get a contradiction, B and not B, and then you infer A. All right, so let's just try some examples of this. All right, so here is an example that's from the text. Suppose we're given L if and only if not O, L or not O, and from that we want to infer L. All right, so you write this up in the standard way. You say L if and only if not O, and L or not O, want L. So what can we do here? How can we get anywhere with this? You look at your premises and you see that there's no way to do direct proof here, right? The two premises give us nothing on their own. You look at your want line isn't a conditional, and so that means that you're probably not going to be able to use conditional proof. The only thing that's left to do is to use indirect proof. So how's that going to work? Well, you assume the opposite of what you're trying to prove. So in this case, that means adding a negation, right? Not L. Okay, so and this is for reductio, and you want a contradiction. So what can you do with the not L? Well, the not L works with this statement here, right? Here we have L or not O, and here we have the negation of the left side of that. So again, that should remind you of the scheme disjunction elimination, right? Here the role of A is being played by L, and the role of B is being played by not O, but it all works out the same. So that means that we can get not O by or elimination lines 2 and 3. Now what can we do? Well, on line 5, we can use the not O to get L. Remember, this arrow goes in both directions, so you can infer this way or you can infer that way. So not O gives us L. And you think, oh, we're done, right? L is what we wanted. So this is biconditional elimination, lines 1 and 4. But hang on a second. L is what we wanted up here. L is not what we wanted down here, and we have to exit the subproofs in order. So we can't just call it quits here. We only know that L is true on the assumption of not L. We don't know that L is true in general yet. So what we want is our contradiction. Fortunately, there's another rule, which the book actually introduced really early on, and we just haven't used at all. It's called repetition. We just mark it there with an R, R3, L, and not L. Now look at this. This is a contradiction, right? You've got L and you've got not L. These two statements are contradictory. So you've shown that the statement L leads to this the statement not L leads to this contradiction. Since it leads to the contradiction, we know that not L can't be true, which means that L is true. Now we get L where we want it. This is L where we want it out here, and this is negation elimination lines 3 through 6. All right. Let's try another one. Suppose we know A and we want to show not A. So this is actually an instance of double negation. And you may be used to just saying not A is A, or just, you contradict yourself twice, you get back to where you begin with. And that's just a rule of common sense. But it is something we need to prove in our existing system. So let's just go ahead and do that. We write A, and we want not A. Again, there's nothing we can do with the current premise, so we can't use direct derivation. We're not trying to show a conditional, so we can't use indirect derivation. We can't use conditional derivation, so we need to use indirect derivation. That means we're going to assume the opposite of not A. And so there are two ways you could do that. You could add a third negation, or you could take one off. Let's just take one off, because three negations is silly. So we say not A, and this is an assumption for reductio, and we want a contradiction. So now look at this. What we want now is a contradiction. We may have thought that we want not A, but we're going to have to set aside this desire to satisfy a more immediate desire for a contradiction. Fortunately, we already have a contradiction. It's just a matter of bookkeeping to get it all in the right place. Right? So the rule is that you want a negation, you want a sentence and its negation at the end of the derivation. So we're going to write an A here, and that's R1, and then a not A here, that's R2. Now we have a sentence and its negation at the end of the subderivation. We can pop out here, and we can write not A. So, and this is justified with negation introduction. You see, we added a negation to what we had before, so that's lines 2 through 4. Now I want to try something more complicated. So far, all of the derivations we've been doing have just involved single subproofs, and generally the subproof is launched at the beginning of the derivation, and when the subproof is over, the derivation is over. But there can be more complicated situations. So let me show you one of those. Suppose you knew not A or B. So you can read this in English, neither A nor B. That's actually equivalent to not A and not B. This is something called De Morgan's law. It's kind of interesting. In algebra, you can talk about distributing like a negation over, or a multiplication over addition. This is kind of like a distribution rule for logic, but what happens is when you distribute the negation, a disjunction turns into a conjunction, and vice versa. So 1, A or B. Want not A and not B. So one thing you could try here is to assume the negation, the opposite of all of this. And I'm going to do this part in pencil because this is a mistake and we'll have to go back and erase it. But let's just see what happens. If we wanted to do the negation of all of this, it would be not A and not B. And we'd say for reductio, want a contradiction. But look, this still doesn't help us. This actually just made life more complicated. I mean, this is a big, complicated sentence. Actually, the thing to... Oh, and we would have done this in a subderivation like that. The thing to do here is, rather than trying to get all of this at once, try to get the two parts of it separately, and then we can put them together using and introduction. So, rather than doing... rather than trying to show... rather than trying to show this whole thing, we're going to first show not A, and then we're going to show not B. All right, so how can we do that? Oh, and look at me. I forgot. This is supposed to be negated up here. See, I just forgot to pull the negation down when I rewrote it. All right, so actually what we're going to assume here now is not the negation of all of that. We're going to erase. And we're going to assume A, which is the opposite of the thing that we wanted over here. So this is for reductio, want a contradiction. We want the same thing, but now we're in a better position to do it. So we've got this line here, which is not parentheses A or B, and we've got A. How can we generate a contradiction? Actually, we're just one step away from it. We have to use that tricky rule of or introduction. Or introduction, line 2. Or introduction's funny because it lets you add anything you want. As long as you know that A is true, you know A or B. You can add any B you want. This could be B or C or D implies Q, whatever. But in this case, we just wanted B. And now to get our contradiction explicit, we repeat over here. So we say A or B, not A or B. That's R1. This is our contradiction. And now out here on line 5, we get not A. Negation, introduction, lines 2 through 4. Well, we're not done yet, but we're halfway there. We wanted not A, and we also want not B. So let's go ahead and do the same thing for not B. We make another assumption. This time we assume B. For reductio, want a contradiction. Right? And we can do the same thing. We can get A or B by or introduction. This time it's on line 6. And we need to repeat this. Now remember, when we repeat a previous line, it has to be one that's open to us. So this is what we want, but it's not in a position that's open to us anymore because it's inside this subproof that ended. So we actually want this one up here. So we're going to be repeating line 1, not A or B. Right? There's our contradiction. That gives us not B on line 9. Not B, so that is negation, introduction, lines 6 through 8. And then finally we put lines 5 and 9 together to get our actual original want line up here. And we get not A and not B. And introduction, lines 5 and 9. Okay, so let's try some problems from the homework. We're going to do with this one. This is a fill-in-the-blank problem. Now, the first blank you've got here is actually your want line. Oh my God, how can we fill that in? I mean, shouldn't we know what we want? Well, you can fill it in because it's down here, right? You know that the line that ends the proof is going to be the line that is in your want line. So it's not A or B, right? And we know, actually, well, so we look at this and we see that this is actually another variation on De Morgan's law. It's actually the same proof we were doing before, but in reverse. Now this time, actually, we don't launch the subproof immediately because there is stuff we can do with our premises, right? We've got not A and not B as one line, and we can break that up. So this can be and elimination on line 1 gives us not A, and then and elimination on line 2 gives us not B. Now, however, we're stuck, right? Because there's nothing left we can do. So now we want to assume the opposite of what we are trying to prove, right? And that means removing the negation here and just getting A or B. So you want a contradiction. So how can we get B from this? Oh, well, we get B from these two lines, right? We're going to have B by or elimination lines 2 and 4. Because we've got the or here, we've got the negation of one side, that gives us the other side. And then the not B is just repeated from line 3. And then on here for line 7, we can say that it is negation introduction lines 4 through 6. Okay, I'm going to do one problem from part C, and I'm going to pick this one here, and I'm choosing it because it allows us to use both. It shows how you can use conditional derivation and indirect derivation together, which is a new thing, right? So our premise is A implies B, and our conclusion is A implies not B implies not A. So what's going on here is we know that A implies B. Well, if A also implied the opposite of B, then A couldn't possibly be true. So let's write that out here. 1, A implies B, and you want A implies not B implies not A. So we can't do anything with our premise. So step 1 is always try direct proof first. But we don't have anything to do with our premise can't do anything, so we can't do direct proof. Now look at your want line. In this case, your want line is a conditional. So we can use conditional proof here. That means we assume the left-hand side and we try to show the right-hand side. A implies not B. So this is for conditional derivation. And you're going to want not A. Well, we still can't get anywhere with these two premises, but we've made a lot of progress. So because we can't do anything else with what we have, we're stuck at the last resort, right? And always as a last resort, you use indirect proof. Now, you want to use indirect proof on your most recent want line. You could try assuming the opposite of this up here, but that, in addition to being complicated, isn't even the first thing you want. The first thing you want is not A. So if you assume the opposite of it, you get A. So this is for reductio, for indirect derivation, and you want a contradiction. Well, now you've got things that work, because you can get B, conditional elimination, lines 1 and 3. I'm sorry, 1 and 2. And not B, conditional elimination, lines 1. Except it's not line 1. You know, I'm being stupid. So 4 is lines 2 and 3. And then this one is lines 2 and 4. There's your contradiction. So you pop out one level, and you have not A. Negation, introduction, 3 through 5. Then you pop out another level, and you get your final want line. A implies not B, implies not A. Conditional introduction, and then you do this whole thing from 2 through 6.